So let's see. So I'm excited about today because we're going to go through the, what's that?
Before you start, I think you did make them right. They are freaking out.
Oh, really? Close the door. If we're going to talk about them, definitely close the door.
They're like, one of the people were like, did you get 4 D's in a row? Yeah. Like, all right, I feel better. I'm like,
yeah, I did. Oh, you make a point. I didn't really scramble. I didn't pay attention to whether I scrambled the letters. Yeah.
That's just how crazy at first. I was like, then I started hearing point group. I'm like, oh, okay.
Yeah. So the pecan test. Yeah.
Freaking out.
Okay. Well.
That makes me feel a little bit better.
Yeah. The flashbacks. Yeah. Yeah. So I gave a test in my other class, and the students are a little nervous about it. Yeah. It's okay. It's okay. Yeah. Yeah. Okay. Yeah. Understatement. And so, and so we are doing some of the things from that class in this class. 2 reasons. One, I think it's good to see it again if you've had that class before. And 2, the numerical approach to solving for spectroscopy specifically today, I'm very excited about because it combines the analytical stuff that we did in calculus, analytical calculus, with the symmetry stuff that's pretty easy, and combines those in Excel. And so you can not only get the selection rules pretty easily, you can do integrals by hitting Control-Shift-Enter instead of all of the integration math that you learned. You can just realize that the integral is a sum. Right, that's what the little integral sign is supposed to indicate. It's like a stretched up S because it's a sum. And that the derivative is just a delta y over delta x. These concepts of the slope, right? And in the old days, when they started out with computers, the computers were slow. And so they had to come up with these approximations, faster ways to take the derivative, faster ways to integrate. But computers are so fast now, and for small systems like a particle in a box, you can just use the basic definition that an integral is a sum and that the derivative is the slope, and you can get all of the results, like the Schrodinger Equation, the selection rules, all of that. So you have to do really no calculus. Calculus is a sum and a slope, and that's it. And you get all of the results that we got out of the analytical methods. And so we're going to go through this exercise that is a laboratory exercise in the undergraduate course. But I just want to talk through this. Even if you've done it, some of you have done it, even if you've TA'd it, there's still some things that I can pull out that I want you to remember. And so we're going to go through that spreadsheet. I give you a copy of it. And I want to point out some things about what we're seeing in Excel as we go through this. So what we have here from Dirac, again, why do we use numerical methods of calculus? He says the underlying physical laws for the mathematical theory of physics and chemistry are pretty well known. He said all of chemistry is known because we know the Schrodinger equation, the wave functions, where the electrons are going to be if we can solve that Hamiltonian Schrodinger equation for the electronic structure of a molecule. But the problem is these equations are too complicated to be soluble, meaning we don't have analytical solutions for them. But we have computers. And so that's where a lot of our research money has gone into. High-power computing is solving these kinds of problems numerically. And so numerical methods are very visual. Because we have all of the data right there for the electron cloud, we can plot it. In our one-dimensional case, we have the wave function, and so we can see it. We don't have to think about it. We can actually plot it. Numerical methods, the analytical solutions only exist for single electron systems. And so we must use numerical methods for anything more complicated than hydrogen or H2+. They've solved that one. Okay. And then numerical methods, they use fast computation of complex problems, so we can do more. So this is the first page of that spreadsheet. And I just want to talk to you a little bit about how this spreadsheet is constructed. You see these banners across the top that kind of tell you, what we're doing in this sort of page. So I've set it up in pages. You can, and the yellow boxes are meant to indicate where you can play with the spreadsheet. So you can go in here and you can change the box length and see what happens to the whole system. The whole page is dynamic. You can change the mass. You can see what happens if in some other universe the electron is 10% heavier, right? Or you could put in a proton, or you could, get crazy and put in a molecular mass and see that the energy levels really crash down to where we can't even see quantization in some of these larger atoms and molecules. But the common thing is the box length you can change, and then the quantum states. Now, I have a high definition or a larger version of this spreadsheet that has 15 quantum states in it. I can upload that to you for you to play with. But get familiar with the steps in this one, and then you can go to the bigger one, and you can really use it as a tool. It has 15 quantum states and calculates 225 transitions, 15 times 15. So, you can really see the full spectrum. In this one, we only have 2 quantum states, so we can only model 1 transition, right? State 1 to 2. Okay. And so you can change those right here. If you were to put, 1 here and 2 there, then you could model the fundamental. If you have 2 and 3, like I have right now, we could model the hot band, the first hot band, right? And so you could even do overtones. You could put 1 here and 4 there, and you could model the overtone. Okay. But just for now, this first page, we're looking at the wave functions. So this is the function that's plotted right here. And then for the next quantum number, the n prime, okay? And so I've plotted those wave functions here, and here they are plotted. Notice it's pretty coarse because we only have, we've got 11 spots, so we have 10 intervals, okay? And so we're only plotting 11 data points here. And so this, again, our box length is 6.75, and so it goes, a little bit more than 3 on either side. And then this is the wave function 2, and this is wave function 3. And you can see that we plotted those, we did the analytical solutions. If you were to plot those analytically, you would see those functions. But what I've also done is, let's look at orthonormality, right? We wanted to wave function times itself, integrated over all space, should equal 1. Okay, and so here I have that first wave function, n squared, and that's plotted here. You see this psi2 squared? That's the blue one. And so if you were to integrate this from the left side to the right side of the box, we would see that that integral here is non-zero. And if we added up, all of these points, like this is 0.1, and this is 0.123, so that's, now we're at 0.4, and then 1, 2, 3, now we're at 0.7, okay, 0.8, 0.9, 10, 11, 12, oh no, 1.2, and then 3, 4, 5. This is a little bit off because this isn't quite 0.3, and then 1.6. So that's our sum over all space times dx. Okay, and up here, I don't think I have dx on this sheet. Oh yeah, here it is, 0.675. So you take that times 0.675, and it equals 1. So that is the integral over all space. You add up the area under that curve times dx. You're modeling these rectangles here. This is the height times dx plus the next height times dx, and you're getting the area under that curve. Straightforward numerical integration. Okay, so sum times dx. Now notice there are some errors here, like this right here is not under the curve. And so some of the homework questions are related to this, that there are numerical errors in integration, okay? And that those errors are reduced if we have a smaller dx. So going from a sum to an integral, dx goes to infinitesimal differences. And so the widths of these little rectangles goes to essentially 0. And that's how we go from a sum to an integral. You follow me? Okay, so the errors aren't because dx is infinitesimal. That would be in an integral. Okay, the errors are because dx is big. Okay, And when you have a big dx, you have numerical errors. So that's part of that. What I'm trying to pull out of that homework question is for you to look at this and go, yeah, we can see the wave function, we can integrate it, it equals 1, but the accuracy of our energies later is going to be off a little bit. Okay, let's look now. I'm going to erase all of this. Let's look at the next one. I won't go through and explicitly integrate this one, but I will just show you. You can kind of see from the symmetry of the function that in this x or psi n times psi n prime, that's this other one. So psi 2 times psi 3. You see we have some positive numbers that will add to our integral, and then we have a negative number here that's going to subtract from it. Then we have a small positive number here and a lot of negative numbers there. And you can see the symmetry that the positives and the negatives are going to cancel out. And so the integral over all space of this one is going to equal 0. Yeah, so if I integrate that over all space, that's equal to 0. Yeah. So we see that they're orthogonal and we see that they're normalized. Okay, now we can do that in numerical form using sum product. So this this formula here is equal to sum product, open parenthesis, and it would be this one here. This is array 1. This block here. So this would be 1, comma 2. Right? This is block 2. So if I take this column times that column and integrate over all space, then I get 0. If I take this column times itself, I get 1. And so you can integrate by taking the product of these two functions, adding them together, adding all the numbers, that's the integral part, times dx. Okay. Okay, and that's your integral. Now you can do the same thing in matrix format, and we'll talk about that next. So can you see the Kronecker delta here though? So you see n and n prime. So if we call the let's just call these here n and these here are n prime. When n equals n prime, you have 1. When n equals is not equal to n prime, you have 0. And so this matrix is a way to show all possible combinations of these two wave functions. Any questions so far? So you can see how we're doing this just numerical integration using either sum product or matrix multiplication. So let's talk a little bit about matrices and arrays. So arrays are arrays of numbers. We also want to talk about a manipulation of those numbers, multiplication of arrays, multiplication of matrices, and then numerical integration. So let's take a little side trip. I'm talking about numerical integration. So any row, column, or block of numbers is an array. Or, it could be a row, it could be a column. And so this right here, when we're talking about matrices, we say row first and then column second. So this right here is a matrix. It's also a vector, but it's a 1 by 3 matrix. And this one is a 3 by 1 matrix. And that's important if we're going to multiply these things. Okay. So I just wanted to make sure that you know we talk about row first and then column. Because if you get that backwards, then you make mistakes, okay, or things don't work. Now let's talk about manipulation of these arrays. So if we were to transpose this 1 by 3, we end up with a 3 by 1. And so what we're doing is we're rotating it on that first diagonal. Now it's a single row, so it's really hard to say that it's a diagonal. But if this were a bigger matrix, it would be a diagonal. Okay. And then if we transpose a 3 by 1, we get a 1 by 3. This is a little bit easier to see when we have, I guess, a multi-row matrix. And so if we transpose this one, look at how it rotates. It rotates around the diagonal. So do you see how that B and D have switched places? So we're rotating around A and E, and they stay put. Yeah, and so B comes down here, and C, B, and F go to the other side. Yeah. Does everybody see that? Yeah. It's important because we need to do this in our spreadsheet to multiply our wave functions. And we'll see some visual examples here. Now, this is interesting because in Excel, this is what's called an array formula. So if I were to, I can do this in Excel, but I need to select all of these cells. So I would select that block with the mouse. And when I select that block with the mouse, the cursor will be up here in this top left-hand corner. And in there, I type equals transpose. And then I select this block here. That goes inside the parentheses, okay? And then I hit this. I don't just hit enter, I hit Control-Shift-Enter because I'm putting a formula into 6 blocks at once, into 6 squares at once. So this is how you use an array formula. Now, it requires knowledge. You have to know what the end result's going to be. So if I'm transposing a 3 by 2, I need to know that that's going to give me a 2 by 3. So I have to select the correct area, type in transpose, put in, select the array that I'm transposing, and then hit Control-Shift-Enter, and it will do it. Okay. So in Excel, you do transpose array, and then you'll see these little curly brackets in every one of these squares. After you're done, if you were to click on one of those squares, you would see this formula in there. Only this word array would be replaced with the reference of this one, like A1 to let's see, B3. Okay, and so it would be that group of numbers. Let's see how this helps us. Okay, so for array multiplication, I can take this 1 by 3 and multiply by a 3 by 1. And so the 1 is multiplied by the A to give this number. The 2 is multiplied by the B to give this number. And the 3 is multiplied by the C to give that number. And notice it's a sum. And so array multiplication, by definition, is a sum. If I take that sum and I multiply by dx, then I've taken the integral. So I can use array multiplication as numerical integration. And so this is a fast way, using matrices, to do numerical calculus. And this is what the Gaussian's using a lot of. It's using a lot of matrix manipulations and multiplications to do these integrations. Okay. And so once again, you have these arrays. You can do sum product. If you just do sum product with those arrays defined inside sum product, then you can integrate using sum product. If we do that with a matrix, then we have a 2 by 3, 2 by 3 times a 3 by 2 matrix, and that's going to end up with this final result. And notice the final result is a 2 by 2, 2 by 2, 2 rows, 2 columns.
The number of columns in the first one has to equal the number of rows in the second.
Yeah, that's right. So we'll see that in the next slide, that these middle numbers have to match. And then the result will be the outer numbers. Okay, but notice what we've got. So this is how matrix multiplication works. If you have to do it by hand, you take this first row, 1, 2, 3, and multiply by the first column, and that gives you this first row, first column number. So first row times first column gives you a single number in the first row and first column of your result. If you take that first row to the second column, then you get the first row, second column number. And vice versa. So then you go to the second row times the first column, you get the second row, first column number. And then the second row times the second column is the second row, second column number. So just work your way through. Very tedious to do by hand. I'm not interested in asking you to do it by hand, but we're going to do it in Excel. But I want you to have an idea of what Excel is doing for you. And in that spreadsheet where I have 200 rows in my wave functions, this is a 200 by 15 matrix. Yeah. Times, and I transpose it, so it's actually a 15 by 200 matrix, times a 200 by 15 matrix. I select all of those, and hit Control-Shift-Enter, and I've done 225 integrals, like that. Okay. And I can see the selection rules, or I can see the energies, and I can see that it's normalized and orthogonal. So you can see all of those things. And so in Excel, we use mmult. That's the function in Excel that would give us. So we would select a 2x2, in this example, a 2x2 result matrix, because that's going to be my end result. Type in equals mmult, and I go select array 1, hit comma, array 2, comma, and then Control-Shift-Enter will give me this 4x4 or 2x2 matrix of 4 numbers. Yeah. So this is the rule. This row by column times row by column. So the inner two rows, the inner two numbers must match. So you see that I did a 2x3 times a 3x2. So those numbers have to match because the rows and the columns are going to be multiplied by each other. So they have to match. And then the result will be the outer two numbers. Okay. And so in Excel, you just type in mmult with matrix 1 and matrix 2. Now we're going to combine these. We're going to put transpose of matrix 1, and we'll see that. So in this case, we have for all combinations of our wave function. So here we now have our wave function, which has got the box is divided into 10 increments, right? And so our matrix has 10, or it's really 11 rows, and we have 2 wave functions, so it's an 11 by 2. But we transpose that, so it becomes a 2 by 11 matrix, and it transposed it. It rotated on the diagonal here. Okay. And so wave function 1 is on top, wave function 2 is on bottom. And I take that 2 by 11 matrix and I multiply it by itself, the original 11 by 2 matrix. Yeah. So this is doing the testing for normality and orthogonality. I'm taking the wave function times itself and the wave function times all the other wave functions. And I get, in this case, a 2 by 2 matrix. So I have a 2 by 11 times an 11 by 2, and then end up with a 2 by 2. Yeah. And this is wave function 1. So the first row here, which is wave function 1 times the first column, gives us the first row column number. And that's 1 times 1, which is 1. Isn't that great? So can you see the Kronecker delta there? Yeah. So you see when wave function 1 is multiplied by wave function 1, the result is 1. And when it's multiplied by wave function 2 or any other wave function, it's 0. Well, we just have 2 examples in this spreadsheet. We just have 2 wave functions. This is going to help you next, like in 2 weeks.
No, this is great.
When you're explaining what's going through. So, and I'll run through this for the class too, just so they have a better feel for what's going on in the PChem1.
Yeah.
Okay. And so this is a simplified way of writing it. Dirac notation, integral over all space for a wave function times other wave functions is the Kronecker delta, which is 1 if the wave function quantum states are equal and 0 if they're not equal. And here we see almost as simply stated, in this matrix format, and we could see the pattern. Okay. And so that's what we see. I've already kind of showed you the orthogonality piece, the plus minuses piece that cancel out. You can also do this with symmetry. So I have a wave function here. This wave function is wave function 2, and so here's the blue one, wave function 2. If I come left to -2 and look at the result, it's up here. And if I go right the same distance, it's an equal but opposite sign. Equal magnitude, opposite sign. So that's the definition of an odd function. Do you remember that? Yeah. So the right side is the opposite sign of the left side. Yeah, so the right side, the blue, look at just the blue one. The right side is the opposite sign of the left side. You see that? That's an odd function. Okay, and so I put that test in here so I can see this. This says odd right here for that wave function. Okay, so this is in the spreadsheet, and you can go in and look. I put the definition. I go left and look at the sign, and I go right and look at the sign, and I have an if-then statement. If they're equal and opposite, that's odd. If they're equal, and the same sign, then they're even. So let's look at the quantum state 3. I go left, -2. I come up here. I go right to +2. Same magnitude, same sign. So that's an even function. So wave function 2 is even. Now we did wave function 1 times itself. So we have odd times odd should equal even. When we come down here, what do you know? Even. Okay. And we see that here too. This is the blue function. If I go left, if I go right, they're the same sign. Okay. And then here, wave function 1 times wave function 2, I have odd times even should equal odd. And it is. Okay. And I go here, I go left, positive, I go right, negative, equals magnitude, but opposite sign. Okay. Yeah, so the symmetry rules you can see right here in the spreadsheet as well. Okay. So that's everything for page 1. That's just analyzing the wave functions. We have a normalized wave function. They're orthogonal to other wave functions. In the spreadsheet, you can play around with it and change your quantum states. Okay, next panel is solving the Schrodinger equation. Now, the Schrodinger equation is given here. Let's see. No, I guess it's not given here. I have to look at the notes. Okay, I should probably put it in here. But it's that integral over all space of the wave function times the Hamiltonian operating on the wave function. So I'm going to go ahead and write it out. So it's, we'll write it in this form. The expectation value of the energies is equal to the integral over all space of the wave function of n times the Hamiltonian operating on the wave function. Okay. And so this right here is the second derivative operator, right? The Hamiltonian, it has the second derivative in it. So we need to take the second derivative of our wave function. And so here I have our two wave functions. I have the first derivatives, and I have the second derivatives. You see the double primes. Prime and double prime indicate derivative, second derivative. And so I went ahead and plotted them here. I mean, you can see the wave function here. Let's just look at the blue one. It starts out with a slope close, a positive slope. And so here's the slope, okay? And then as it starts to go to the right, notice the slope starts to get more gradual. It starts to go through 0. And so the slope should cross 0 somewhere around here, and it does. Okay, and then the slope starts to become more and more positive. It's negative here, so this is negative slope here. That's the steepest part right at 0. And then it goes through 0 again, so the slope goes through 0 again, and then it ends on a positive note. Okay, and so it ends on a positive note. So again, that's just taking the change in y dividing by the change in x. And we get the first derivative. If we do that again, so here we have this, we take the slope of the slope. So this it starts out really at 0. You can't really see that, but it starts at 0, and then it starts to get negative. So it goes below the axis. It crosses 0 here. The slope is flat, so it's crossing 0, and then it's steep again, it's positive, and then it goes to 0 here. Okay. Now notice numerically when we take the slope, how do I get the slope of this number right here? Well, I've got to actually calculate a number over here to see what that slope is at that number. And so every time we take the derivative, we lose a couple of rows. And so that's why, if you'll notice on over here, I've extended my wave function outside the box. Shh. Okay, just for numerical sake, I've gone outside the boundaries of the box to see what the slope would be at the box edge. Okay, and so we went outside the box 2 increments, because when we take the first derivative, notice we lose that row. And so this is the first derivative, then we take the second derivative, we lose that next row. And so that way I have a number for every spot inside the box. Okay, and this is just again just a part of the way we're doing numerical integration. But now I can take once I've operated on this first derivative operated on the wave function, I have the second derivative of that wave function, and I have a bunch of constants that come out front. And so those constants come out front, those are going to be my energies here. And then I have the wave function times that second derivative wave function integrated over all space. And so I can do my matrix transposition, or transpose and matrix multiplication. So I have psi double prime here and here, and I have the wave functions here unperturbed. So this is the matrix multiplication for the Schrodinger equation. I take the wave functions, just psi and then psi double prime, and I have those two blocks. And I do the transpose of my wave functions to make it a 2 by 11, and then I multiply by the second derivative of my wave functions, and I get all of the combinations. Now, I'm only interested in the diagonal of this matrix. Those are the eigenvalues. Okay. And so these right here are the eigenvalues, which happen to be the energies of this. So whenever n prime, if there's no n prime there, but whenever n prime equals n, then we end up with the energies of n. Okay. When n prime doesn't equal n, then we end up with a sum of an odd function, and it all cancels to 0. Okay, so the orthogonality comes in to where we just have diagonals that are our eigenvalues. Let me pause here just for questions. So all of those constants that come out of that second derivative come out front because they're constants. And when we take the integral, the wave functions times its second derivative essentially equals 1 or 0, and it's the constants that give us our energies. Let's go back and look at our second derivative. Notice that the amplitudes of these functions, the wave functions, the amplitudes are about the same, aren't they? Okay. And then after I take the second derivative, notice the amplitude of wave function 2 is about this big, but wave function 3, the amplitude is even bigger. Do you know what that is? What that's telling you? When we took the second derivative of our wave function, we had a sign change. Notice the blue curve here is the same blue curve, only it's inverted. There's a minus sign, and there's a minus sign in the Hamiltonian, so the minus signs cancel. Okay, so we get a positive energy value. But the amplitude is essentially that wave function times a minus 1 times a bunch of constants. And so the amplitude of the second derivative is what's giving us our energy. So the more curvature we have, the bigger the amplitude of our second derivative. And so we can kind of see that the amplitude is proportional to our energies. Because we have more curvature in the n equals 3 wave function, we have a higher amplitude in our second derivative. I'm just kind of showing you what I see when I look at these curves. Okay. Makes sense. Yeah. I mean, that may be a nuanced point. I don't know that the undergrads would pick up on it, but I just wanted to kind of show you there's more curvature. And how do I know there's more curvature in the orange function? There's more nodes, right? It goes through 0 twice, whereas the n equals 2 wave function only goes through 0 once. So it curves more. So that curvature is proportional to energy. The second derivative is the curvature. And so because there's more curvature, we have a larger amplitude in our second derivative. And then that amplitude is a constant value that comes out front, which is our energies. So we end up with these energies right here. So these are the energies from the matrix multiplication. I've collected them in a table here. And so this is the numerical energy for n equals 2. This is the numerical energy for n equals 3. These are the analytical energies. So these are actually the h squared n squared over 8ml squared. Put in exactly the length of the box and the mass of the particle, the quantum state, Planck's constant. And so these are, because this is a simple one-dimensional system, these are the true energies. This is This is using analytical calculus, infinitesimal dx. These are the true energies. The analytical solutions are the true energies. And so when we talk about error here, it's the numerical side that's got the error. Okay, not the analytical side. And so this is saying our numerical integration is off by 12%. And then at quantum state 3, it's off 26%. And you know why, don't you?
Number of steps.
Yes,
How many times you
we
buy
only
it.
have 10 increments in our wave function. And that's called our grid. Our grid density. There's our grid density is low, meaning we haven't taken our box and divided it into a fine grid. We have a very coarse grid. Do you understand coarse versus fine? Think of particles of sand, and a fine powder, or sugar. You can have coarse sugar or you can have powdered sugar, which is really fine. We've taken our box and we've divided it into coarse steps. We only have 10 increments. We have 11 points, but 10 increments. And if we were to take that and divide it by 100 steps or 200 steps, our error would drop dramatically, because our columns that we're integrating, the area under the curve, would have much fewer triangles that are sticking outside the curve. Okay, so if we were to integrate this, this is our column, and this area here is error. It's not under the curve. We're looking at the area under the curve, and if there's pieces sticking above the curve, that's not inside our function. Okay, so that's some discussion on the errors. Now let's go to solving the selection rules. So we have orthonormal wave functions. We've solved for the energies. So we have the energies of our wave functions. Now we need to see if the transition from 2 to 3 is allowed. So we can solve for the transition dipole moment. So we have our wave functions here. Let's just look at this n equals 2 curve. I'm going to multiply it by x. And so x, if I have, y equals x, then it's this diagonal line here. And so this is, again, f of x equals x. And so here I have negative numbers for x and positive numbers for my wave function. And so this is x times psi, and you see that it's negative here. And here I have positive x values times a negative wave function value, and so it's negative as well. Okay. But the point is it's even. Okay, I have an odd function here, and I have an odd function here, and I have an even function there. Odd times odd is even. Okay, so that still works. Taking the n equals 3 state and multiplying by x, you get this orange curve up here. It's got kind of a funny shape, but you can see it's odd. So I had an odd function, I had an even function down here times an odd function, and I end up with an odd function up here. Now, using matrix multiplication again, I can go through and I can take my wave functions, this 2 by 11 matrix, and multiply by the product of x times psi. And so I have, wave function 2 times x times wave function 2 summed over all space. There was an odd function integrated over all space, you get 0. Okay, I can take this x equals 2, or wave function 2, and multiply by x times wave function 3. I end up with an even function, and I end up with a non-zero result. And so can you see the selection rules? So at least in this particular case, delta n is equal to plus or minus 1. Because I went from 2 to 3 or from 3 to 2. That's all I can say from this. I can't say the 5 or the 7 or anything like that. And so delta n is plus or minus 1. Delta n can't be 0 because here's 2 going to state 2 and it's 0. Okay, so we can't interact with light and absorb it and stay at the same level, right? Because if you absorb that light, you're going to change. Okay. So hopefully you can see the selection rules there. And then those values were squared because, again, we wanted positive values, and that's proportional to the intensity. So if we were to do this like my high definition sheet, 225 transitions, this is what we see. So instead of a little 2x2 matrix, this is a 15x15 matrix. And can you see the patterns? Look at the selection rules. So this pattern emerges where 1 going to 2 or 2 going to 1 is non-zero. You see that? 4 going to 5 is non-zero. So you can see these diagonals are setting up our selection rules. What about 3 going to 3? So, 3 going to 3 is 0. Yeah. Okay. 6 to 6 is 0. And so we can see the integrals are 0 when delta n equals, plus or minus 2, 4, 6, 8. Right. Here's 2 going to 4. So let's connect 2 to 4. That's 0. So that's a change in 2 quantum states, and that's forbidden. And so these non-zero diagonals are giving us our selection rules. That is gorgeous. This is how I knew that this whole particle in a box thing would work, was when I was playing around and I thought, I wonder if I do this in Excel. This was 10 years ago. I wonder if I can get the selection rules out of Excel. And so I had plotted my wave functions for class just to make PowerPoint slides. So I had my wave functions in Excel, and I had thought, what if I tried the selection rules? And so I just thought, can it be that simple, just to take the x-axis times my wave function, and then multiply that by my wave function, add it up, multiply by dx, and see if I get a non-zero result. And I did it, and I saw these patterns, and I was blown away. Because analytical calculus tells you when the delta n's will give you non-zero results and 0 results. And I had a pretty good faith in analytical calculus, as long as I don't drop a negative or forget to cancel something, right? But in Excel, I thought it can't be that easy. Can it? It is that easy. I can just take the x-axis times my wave function, and then multiply that by my wave function, and sum it up and times dx, and I get the selection rules. So all of these diagonals are our selection rules. Now they get dramatically smaller, and you can see from analytical calculus that as delta n is in the denominator, it gets really small fast. It's in delta n squared in the denominator. So the intensity really drops with delta n's. So they show 0 because I'm just showing you to 1 decimal place, but they're non-zero. Now let's do the last bit. Let's plot the simulated spectrum of this transition. It's going to be kind of boring because we just have one transition. We have 2 wave functions, only 1 peak. Okay, but this is where we get into the transition equation. So we've calculated the quantum states here. We have n equals 3, n equals 2. We have the energy of the upper state, energy of the lower state. You can calculate delta E, and then using this equation, calculate the wavelength. So that's our transition wavelength, using the transition wavelength equation. Now we need to calculate our intensity. So we have the Boltzmann factor, we have the transition dipole moment integral, and then we're going to go ahead and put a Gaussian on this. So we need to have molecules in the lower state if we're going to calculate our going to have a transition from state 2. We need to have molecules in there. And so at this high temperature, this is the relative population of that state. So if I have 100 electrons in the ground state, I have 94 electrons in the second n equals 2 state. Okay, so this Boltzmann is our thermal population. It's a little different than it was earlier in the notes. So I'm going to go ahead and write it out here. This is the degeneracy, and it's this right here. It's E of whatever state you're in minus the state 1. So we're looking at the difference above the ground state divided by KT. So that's the important piece right there. And I asked you a couple of questions in the homework. to calculate this. And so we have that, and in the, I've changed it in the spreadsheet. This should be E1, not E0. Because the quantum state in a particle in a box can't go to 0. So typically I write E0 for the ground state, but for a particle in a box, it's n equals 1. So it should be E1. Okay. And so in a couple of places here, it said E0. Yeah, down here, this should be E1. Okay. And so we're taking the energy of the lower state, so there's 319, subtracting 79, putting that into the Boltzmann factor, dividing by KT, make sure your units cancel, changing that sign, doing the exponential, and G of n equals 1 for all of these states. So that's how we calculate the Boltzmann factor for the n equals 2 state. Then we have the transition dipole moment integral result, which is here. It's brought over from that other part of the spreadsheet. And then we have the Gaussian. Now this goes down 200 rows because I wanted a really nice smooth spectrum. And so we have the wavelength, we have the Gaussian line shape here, which is given in the line shape lecture notes. I have some things up here, the spectral line width. So this is our spectrometer resolution. So notice how when we go to simulate the spectrum, we have things like temperature dependence. We have things like the spectrometer that we're using. So there's things that are based on the wave function, which is the underlying science, and then there's things based on the instrument and the room, like the temperature and how good a spectrometer we have. But this would be the transition centered on around 300 nanometers for this particular transition, n equals 2 to 3. At a really high temperature. And now, because n equals 2 is not the ground state, if you were to drop that temperature to 1, this peak would go away because the intensity would drop to, the Boltzmann factor would drop to a really, really small number. Okay. If you're doing the fundamental, then it's essentially e to the 0, which is 1. So if you have e of 1, let's see, minus e of 1, this goes to 0, and so this goes to 1. So at 0 Kelvin, you still have a peak. You still have the fundamental. Okay. And that's why we like to use low temperature, because all of the hot bands go away. And we're left with only fundamentals and only the first and second overtones, but not the hot bands of those overtones. So the spectrum really simplifies when we lower the temperature. And so that's everything that we have in the numerical solution for the UV-Vis spectrum for an electron in a box or particle in a box. We've gone through the wave functions, orthonormality, we solved the Schrodinger equation, we solved the transition dipole moment integral, looked at thermal population of those levels, and put it all together with a Gaussian line shape, and that's how you get a simulated spectrum. Now, next time we'll go through the high resolution or the high definition spreadsheet, and then we'll look at what we call spectral convolution. And so I'll unpack that word next time. So talk to you later.